Section 8.3 then, the second moment of area. This is the definition. So we've got the second moment of this delta A, this small area, about the axis PQ is r squared delta A, where r is the perpendicular distance from the axis PQ to the portion delta A. Okay, we're going to suppose delta A is sufficiently small so that this distance is fine. And it's just from here to here. So for A, the area, the total area then, we can add up all these second moments of these small areas to find the total second moment of area for the entire plane lamina made up of these little segments. So the second moment of area then is sum all these delta A's up, r squared delta A's. But the accurate answer is when you take the limit of delta A's tending to 0. And you get the answer by integration. So IPQ then, the second moment of area of this laminar strip about the axis PQ, written as IPQ, is the limit as delta A tends to 0 of all these segments. In other words, it's the integral over the area of r squared dA. So, with those principles in mind then, let's have a look at the first example. We've got a thin strip. We've got a distance, perpendicular distance c, and here's our little delta A's here. So the IPQ then, using that formula from above, will just be the integral of r squared delta A's. So we've got them here over the entire area of this strip. Okay, so the c squared is a constant all the way up through the entire delta A's for all of them, so that can come out of the integral. And it's just the integral of the delta A of the area. And when you sum up all the little delta A's, you actually end up just with the area of the entire laminate, plane lamina, which is A times H. So that's what we end up with. The formula then for the second moment of area of a thin strip is the area of the strip times its distance squared away from the axis about which you're taking the second moment of area. Example 2. So here we have a rectangular lamina, length A by B, about axis PQ. So we divide it up into these small strips parallel to this axis PQ, and these are like the strips that we had in the previous section. So we know the second moment of area about the axis PQ for the strip, don't we? The formula said above, it was area of a strip times the distance squared. The area of the strip is delta x times x. Is A, that's the length, times the thickness, A delta x, times its distance squared, perpendicular distance squared. So that's ax squared delta x. So we need to sum all these strips from this value all the way up to this value. They need to be summed, don't they? So x goes from here, the strips up to here. So from minus b over 2 to the x value of b over 2, we sum up these ax squared dx's, don't we? That's just an integration, raise the power, top value, take bottom value, work it out, we get this formula here for a rectangular lamina, ab cubed over 12. And here's the formula here. And that's about of length A parallel to the axis PQ and other side length B. It's ab cubed over 12. Let's turn our attention now to examples 3 and 4. Here's our general formula for a rectangular strip. The second moment of area about PQ is equal to AB cubed over 12, where A is the distance parallel to PQ and B is the distance of the rectangle perpendicular to PQ. So with that thought in mind, IAB will be a 12th. A would be the distance along parallel of AB, which is 4. And B would be the perpendicular to AB, and that distance is 6, so it would be 6 cubed, wouldn't it? So 4 goes into 12 3 times, 36, and there's a 2, because the 3 goes into one of the 6's twice, so 2 36s are 72 units. ICD, so here we've got the formula again, 1/12 of AB cubed. A is parallel. So along CD, A is parallel as 6, times b cubed, the perpendicular is 4 cubed. So again, 6 goes into 12 twice. One of the 4's goes into 2 twice, and that leaves 16 2's is 32 units. Okay, and that's the second moment. About CD of that area. Now we'll look at an example for it. Once I is CD, here we got this T-shaped thing which we can divide into two separate areas. We could call that A1, say, and that A2. So ICD will be equal to 1/12 AB cubed for this area. Well, A is the 3 because it's parallel. Oh no, the 1 is parallel to CD. So the A is 1. And the B is 3, and that would be 3 cubed, wouldn't it? AB cubed, and a plus. Now the next area would be 1/12, and this area here now, A2, the parallel, the A, would be 2 units, and the B, because that's 1, and that's 1 in the picture, this would be 1, so this is a 1, so it's 1 cubed. Okay, good. So that would be 27/12 plus 2/12, which is 29/12, which is 2 5/12. Which is, well, if you tap it in the calculator, you get 2.42 to 2 decimal places. Units. So that's the SMAs. Second moment of areas for those example 3 and example 4. So here's some standard results for rectangulars. A rectangle, we've done this one earlier on. AB cubed over 12. For a circular plane laminar of radius A, pi a to the 4/4. And a semicircle is half of that, pi a to the 4/8. And a triangle of base A and height h, where we've got this axis here, is AH cubed over 36. So let's have a look at example 5 then. We've got this shape here, where this circle's been cut away from this rectangle. So first of all, the second moment of area about this axis then here, PQ, well, let's consider the whole rectangle, and then we'll cut out the whole and take that away from this rectangle, so to speak. So a bit of subtraction is needed. So what is if this were a simple rectangle, it would be 1/12 of AB cubed. A would be parallel, so that would be 10. And B is 10, and that would be perpendicular, and that would be cubed. So that's the whole rectangle, but we need to take away from that the second moment that this would have produced, because it's not there. So what have we got here? It's a circle, radius 2, so it's pi, minus pi a to the 4, so it's pi 2 to the 4 over 4. Okay, so that's 10,000 over 12 minus 2 to the 4, which is 4 pi here. So that equals, if we tap it in the calculator, we'll get 821.